Welcome back to JVM Internals Crashcasts. I'm your host, Sheila, and today we're diving deep into the fascinating world of method invocation and return in the Java virtual machine. Joining me as always is our JVM expert, Victor. Victor, are you ready to unravel the mysteries of method calls?
Absolutely, Sheila. I'm excited to explore this crucial aspect of JVM internals with our listeners. It's a topic that's at the heart of how Java programs execute.
Great. Before we dive in, let's remind our listeners that we're currently in Level 3 of our series, focusing on JVM expert topics. We've just covered bytecode and the JVM instruction set in our previous episode. Today we'll be building on that knowledge to understand how methods are actually invoked and how they return.
That's right, Sheila. And for our listeners, it's important to have a basic understanding of Java methods, stack memory, and JVM bytecode before we proceed. If you need a refresher, I recommend checking out our earlier episodes on these topics.
Excellent point, Victor. Now, to kick things off, I have a quiz question for our listeners. Here it is. In terms of performance, which type of method invocation is generally the fastest? A static method call, an instance method call, or an interface method call? Think about it, and we'll reveal the answer at the end of the episode.
Ooh, that's a great question, Sheila. It really gets to the heart of how different method invocations are handled by the JVM. I'm sure our listeners will have some interesting thoughts on this. Without giving away the answer, I can say that the performance differences between these types of calls are closely related to how the JVM resolves and dispatches methods.
Indeed, Victor. Now, let's start with the basics. Can you explain what happens when a method is invoked in Java from the JVM's perspective?
Certainly. When a method is invoked in Java, several things happen behind the scenes. First, the JVM needs to locate the actual code for the method. This process is called method resolution. Once the method is resolved, the JVM creates a new stack frame for the method call. This stack frame contains local variables, operand stack, and a reference to the constant pool of the current class.
That's interesting. So it's like setting up a new workspace for each method call. But I'm curious, are all method invocations treated the same way by the JVM?
Great question, Sheila. Actually, there are different types of method invocations in Java, and the JVM handles them differently. The main types are static method calls, instance method calls, interface method calls, and special method calls, like constructors or private methods.
Could you break that down for us? How does the JVM distinguish between these types of calls?
Certainly. The JVM uses different bytecode instructions for each type of method call. For static methods, it uses the invoke static instruction. Instance methods use invoke virtual, interface methods use invoke interface, and special methods use invoke special. Each of these instructions triggers a different method resolution and dispatch process in the JVM.
That's fascinating. It reminds me of a restaurant with different ordering systems for takeout, dine-in, and catering. Each type of order is processed differently, but they all result in food being prepared and served.
That's an excellent analogy, Sheila. Just like how a restaurant might have optimized processes for different types of orders, the JVM has optimized these different invocation types for performance. For instance, static method calls are generally the simplest because the method to be called is known at compile time.
I see. So if static methods are simpler, why don't we just use static methods for everything?
While static methods are indeed simpler and potentially faster, they have limitations. They can't access instance-specific data directly, which is crucial for object-oriented programming. Instance methods, on the other hand, allow for polymorphism and are resolved dynamically at runtime, which provides more flexibility but can be slightly slower.
That makes sense. Now, you mentioned earlier that the JVM creates a new stack frame for each method call. What happens when a method returns?
When a method returns, the JVM destroys the stack frame created for that method. If the method has a return value, it's placed on the operand stack of the calling method's stack frame. The program counter is then updated to the next instruction in the calling method.
Interesting. It's like cleaning up the workspace after finishing a task. Victor, How does this process compare to method invocation in other language runtimes, like Python or JavaScript?
That's a great question, Sheila. While the general concept of creating a new context for method execution is similar across languages, the specifics can vary. For instance, Python uses a call stack similar to Java, but it doesn't have the same distinction between static and instance methods at the VM level. JavaScript, with its prototype-based object system, handles method dispatching quite differently. However, modern JavaScript engines like V8 use sophisticated techniques to optimize method calls, which can make them competitive with statically typed languages in many cases.
Fascinating. It seems like there's a lot of complexity behind something as seemingly simple as calling a method. Are there any common pitfalls or misunderstandings developers should be aware of?
Absolutely, Sheila. One common misunderstanding is about method overriding and overloading. Developers sometimes confuse these, which can lead to unexpected behavior. Another pitfall is excessive use of interface method calls or deep inheritance hierarchies, which can impact performance due to the more complex method resolution process.
Those are great points, Victor. Do you have any tips for developers to write more efficient code in terms of method invocations?
Certainly. First, use static methods when you don't need instance-specific behavior. Second, be mindful of the depth of your inheritance hierarchies. Third, consider using final methods or classes where appropriate, as these can be optimized better by the JVM. Lastly, remember that the JVM's JIT compiler is very sophisticated and can often optimize your code, so focus on writing clear, maintainable code rather than premature optimization.
That's excellent advice, Victor. Now, before we wrap up, let's reveal the answer to our quiz question. Which type of method invocation is generally the fastest, static, instance, or interface?
The answer is that static method invocations are generally the fastest. This is because they can be resolved at compile time and don't require any runtime lookup or polymorphic dispatch. Instance methods are typically next fastest, followed by interface methods, which require the most complex resolution process.
Thank you, Victor. That's been an incredibly informative discussion. To summarize the key points for our listeners. 1. The JVM handles different types of method invocations, static, instance, interface, and special, using different bytecode instructions. 2. Each method call creates a new stack frame, which is destroyed upon method return. 3. Method resolution and dispatch processes vary depending on the type of method call. 4. Static method calls are generally the fastest, but each type has its appropriate use cases. 5. The JVM's JIT compiler can significantly optimize method calls, so write clear code first and optimize only when necessary.
Excellent summary, Sheila. I hope our listeners found this deep dive into method invocation and return enlightening.
Indeed. In our next episode, we'll be exploring exception handling mechanisms in the JVM, another crucial aspect of Java program execution. Don't miss it. And remember, if you've enjoyed this episode, please subscribe to JVM Internals Crashcasts and leave us a rating. Your support helps us continue bringing you in-depth explorations of JVM internals. Until next time, happy coding.